In this video, I want to introduce algebra. Now, algebra is just a way of representing numbers in general terms. So if we can imagine a number 5 and multiply it by another number, for example 2, then we write 5 times 2. Just put my cursor onto the screen. It's not really a cursor, but it works. So 5 times 2, this is the same as, so 5 times 2, it's 2 5 times. 2 plus 2 plus 2 plus 2 plus 2, which is equal to 10. So what 5 times 2 is saying is, take the number 2 and add it to itself 5 times, and we get 10. It's like shorthand. Instead of writing all of this out, we can just go 5 times 2. That's actually the same as 5 plus 5. We could do it the other way. Instead of writing all the 2's out 5 times, we could write out the 5's twice. Get the same answer, 10. So it's 2 5's, or if you like, it's 5 2's. It's the same thing. So multiplication seems to be related to addition. It's it's a way of efficiently adding up the same number over and over. So instead of saying 2 plus 2 plus 2 plus 2 plus 2, we say 5 times 2. There's 5 of them, and the number is 2, so it's 5 times 2. So we can see that 5 times 2 is the same as 2 times 5, which is 10. That's actually important to us. I picked 5, but I could have picked any number. I could have picked a 2 or a 7 or a half or 41, or we just picked 5. I'm not being very complicated here. I'm not taking minus numbers or very strange numbers you get in further mathematics. I'm just taking straightforward integers, simple integers. 5 is a straightforward number. We have 5 fingers, and that's all I mean. We have 5, and it's 5 times 2. I picked a 2. Same thing. I just picked 2. Why did I pick 2? Well, why not? It's just a number. I could have picked 3 or any number, but it works. It works for 2, so it works for 3 as well. I just have to write more numbers on the slide. So it's just 5 times 2. Now, since these were any numbers, I could have called them, instead of calling it 2, I could have called it A. And instead of calling it 5, I could have called it B. So A could equal 2 and B could equal 5, and A multiplied by B is written as AB, which obviously is the same as BA, because we've just shown this up here. When I reverse them, I get the same number. So AB down here is the same as BA. So I'm starting to work in general numbers. These could be any number. I'm trying to establish the relationship between the numbers, and I'm using symbols here, A and B in this case. And we're just looking at this idea of multiplying 2 by 5, and instead of saying 2, I'll take it in general. It could be any number, as I said. It could be a half, or 27. Make this 27. 27 multiplied by 41. Just get a big number. But it'll be the same thing, AB. So it'll be 27 times 41 is equal to 41 times 27. Same thing. So it's the same as. So look back to this principle up here that we established a few moments ago to show that we can reverse this. We can reverse AB to get BA, and we'll still get the same number, the same answer. So BA is the same as AB. Note here, we don't write A times B or A multiplied by B. We don't write them as AXB, because that was too confusing in algebra. We've introduced a new letter, X. Now, technically, in algebra, I suppose that would mean A times X times B. But X is not a number. X is an operator. So we don't write the X. It's too confusing, so we just get rid of the X. And what we do instead is we write, to multiply, we write AB. It means A times B. So we don't write AXB. AB is our times. Sometimes we can put expressions in brackets, and once the brackets are touching, that means multiply as well. We'll see that later. But for the moment, AB is the same as A times B. That's all we need to know there. Let's look at other arithmetic expressions. We know that AB, where we know about AB, I should say. So if A is equal to 6 and B is equal to 2, then AB is equal to 6 times 2. It's multiplied. AB is multiplied A multiplied by B. So it's 6 multiplied by 2, which is 12. So AB is 12 if A is equal to 6 and if B is equal to 2. Likewise, if A is equal to A over B, and this time it's equal to A over B, i.e. A divided by B. So very, very straightforward. If that's the case, and again A is equal to 6 and B is equal to 2, then Y will equal to 6 over 2, making Y 3. We also have numbers multiplied by themselves, and these are squared numbers. So a squared number is when a number is multiplied by itself, in which case we write a little 2 on the top, just up here on the top right. So we'd call that A squared, squared term. It's also known as the index number. In this case, the index number is 2. In other words, it's 8 multiplied by itself, 8 multiplied by 8. So when we see a squared number, we just take the number and multiply it by itself. If that was 6 squared, we'd have 6 times 6. 5 squared would be 5 times 5. 8 squared is 8 times 8. This idea of writing little numbers on the top right, like here's 5 little 4 on the top right, this is a good shorthand way of doing things like this. We have 5 times 5 times 5 times 5. We have 5 multiplied by itself 4 times. We read 5 with the little 4 on top sometimes as 5 to the power of 4. The small 4 at the top is called the index number. So what we've got now is a new terminology. We could have a little 2 on top, in which case we call it a square. If it's a little 2, it's squared. 8 squared is 8 times 8. I haven't got it down here, but if there was a 3, we'd have 8 cubed. 8 times 8 times 8. But once we get above 3, we call it to the power of. So 5 to the power of 4 is this number here. We don't generally say 8 to the power of 2. We'd say 8 squared. It's just language. This is nothing really to do with mathematics as such. It's just the way we say things. So it's language. If we look at 8 squared again, 8 times 8 is equal to 64, and we have this on the square here. Now if I just divide it up, not very precisely by the look of it, but if I divide it up into little squares, I just draw, hopefully they're not really equal, but technically I suppose they should be. But here we've got 8 down. I hope we have 1, 2, 3, 4, 5, 6, 7, 8. Yep, 1, 2, 3, 4, 5, 6, 7, 8. And 8 across. Good. So we have 8 across and 8 up. And if you count all the squares in here, I suggest you trust me on this, we'd have 64. 8 times 8. So there's 64 squares there. And that's the idea. 8 squared, 8 times 8, 64. So, squared numbers. 8, little 2 on top, means 8 squared, 8 times 8. 3, little 2 on top, is 3 times 3. 3 squared. X is any number with a little 2 on top, is x squared. That's x multiplied by x. Note, we write x squared as x dot x. It may be confusing to write, as it is xx or xxx. So sometimes, so it's multiplied, we might write x dot x, just that times that. There are different conventions in this, and really you need to look at which textbook is using what convention. Sometimes you do see xx, and sometimes you'll see x in a bracket and the other x in a bracket, and the bracket's just touching, and that also means multiply. So just be careful. X squared is x times x, but sometimes it's written slightly differently. So we could write x bracket x, or even x dot x to mean x multiplied by x. Both of these are acceptable. Provided we understand what's going on, it's acceptable. So we should be able to read it and understand that this means x squared here. Now let's look at simple equations. See if we can move from general points about algebra to just simple equations. So if y equals 2 and x equals 5, then y equals x squared minus 3. Now if that and that, then we'd say that, okay, for the moment. Now y equals 2, x equals 5. So we'd have 5 squared, take away 23. So we'd have y is equal to 2, x is equal to 5, 5 5s 25, take away 23. So we have 25 take away 23, 2 is equal to 2. So it's correct. That's not really much of an equation, because the answer is being given to us. All we need to do here is to confirm that the answer is right, that in fact y equals 2. That's what we need to show. When we deal with equations, there is a rule that we should never forget. Whatever we do to one side of an equation, we must do exactly the same to the other side. Otherwise, we'll upset the equation. It won't be a balance anymore. So whatever we do to one side, do exactly the same to the other side. If you don't do that, it'll be an inequality. One side will be bigger than the other side. We'll have manipulated wrongly, so we won't have an equation anymore. So if 2x plus 3 equals 17, what's the value of x? We need to find what this magic number x is over here. We know that 2x plus 3 is equal to 17, so how do we go about this one? Well, try to imagine it as a balance. So here on one side of the balance we've got 2x plus 3, on the other side we've got 17. And it's balanced. Because it's balanced because it's equal. The equal sign tells us this is balanced. Here we've got 2x plus 3 and we've got 17. Now, what we need to do is take off the 3 here for a moment. Well, if you take off the 3, this side is, try to imagine it as lighter. We've taken 3 off, so it'll tip up. It won't be a balance anymore. Now it's an inequality. The 17 will tip it down. We've taken the 3 off. We've just got 2x left here, so the 17 will cause it to tip. What we need to do to get the balance back is, we took 3 off here, we need to take 3 off here. So now we've got the balance back, because we've got 17, and we take away 3, we've got 14 here. So now we've got 2x equals 14. It's balanced. This is balanced up here on the top, and this one's balanced. So we're still got an equation now. Here it wasn't an equation. Here it was an inequality. We had done something to one side and we hadn't touched the other side. Whatever you do to one side, you must do the same to the other. So in this case, we took away 3, we take away 3 here. It's back to balance. We need to get rid of the 2. So if you divide this side by 2, we just get 1x, if you like, x. 1x is just x. And you have to divide this side by 2. Well, 14 divided by 2 is 7. So x equals 7. The answer up here to this expression is, what's the value of x? Well, the value of x is 7. You can always prove it's right, because you could say, well, if x is 7, then 2 times 7 is 14. 14 plus 3 is 17. And that's what we got. So this illustrates that we need to balance the system. So we're going to check it. Then what we'd have to do is just simply go through like I've done before. We have 2x plus 3 equals 17. Here we got 2x plus 3 minus 3, so we'll take away the 3. That's what we did. 2x plus 3, take away the 3 to get rid of the 3 here. So we got 17, take away the 3. That will just leave, if we take plus 3 minus 3, it's just gone. It's gone. Equal to 0. We had 3, we reduced it by 3, so it's vanished. Now we've got 2 left, 2x, I should say left, 2x. And over here we had 17. We took 3 away from the left hand side, we have to take 3 away from the right hand side. So here's 17, take away 3, leaving us 14. So you've got 2x equals 14. And if you divide the left side by 2, you divide the right side by 2, so x equals 7. Now, let's have another quicker look at equations. Look at this one. Here we've got 5, and the 5 is tipping up to 4. So the 5 here is bigger than 4. So this is tipped up. It's sideways. When we say something is bigger than something else, greater than, we say 5 is greater than. We use this symbol here. That means greater than. The 5 is bigger than the 4. So note, the sign here is greater than. Make a note of that. So 5 is greater than 4. Now to make it balance, we need to add 1 to the 4. So we get the balance back, we take 5, we have 4 plus 1, which returns the balance. So this little exercise introduces us to the concept of greater than, and this sign here. Make a note of that. Now, inequalities. Well, let's make 4 sets of numbers. Make the numbers in the x column greater than those in the y column. So here's 2 columns of numbers, x and y. And the numbers in the x column are greater than the y one. So 8 is greater than 3, 2 is greater than 1, 5 is greater than 2, and 6 is greater than 5. We write 8 is greater than 3, which it is. It's bigger than 3. And we read it as 8 is greater than 3. Straightforward. Likewise, 2 is greater than 1, 5 is greater than 2, and 6 is greater than 5. We could say that all the values in the x column, this column here, there are two columns of numbers here, x and y, this is one column. We could say all the values in the x column are greater than the corresponding values in the y column. So let's summarize so far. Equalities. X is equal to x, or x equals 2, whatever we're given. We know that x is equal to x is always equal to itself. So if x is 1,000,000, x is 1,000,000. That's all we can say. If x is 10, x is 10. Sometimes it has a particular value, so we have x equals 2. So we know, if we're told that, and that is true, x equals 2. It's not equal to 3, it's equal to 2. If it's equal to itself, that's true for any value. So x equals x, that could be 50 equals 50. But x equals 2 is a unique value. We also have inequalities. X is greater than 5. Again, x can be any number greater than 5. For example, x could be 6, or 5.1, or 256, or it can be any number. So x is greater than 5. We could have, say, x equals 2. Well, in that case, if x is equal to 2, 2 is not greater than 5. So this is where we have problems. We need to be absolutely sure that the inequality is in fact an inequality, and that the values on the one side are greater than the values on the other side. Sometimes we get x is greater than 5 or it's equal to 5. So it can equal 5 or it can be greater than 5. For example, it could be 6, or it could be 5.1, or it could be 256, but it can also be 5. Back up here on this one, x is greater than 5. It can't be 5. It has to be some number 6, 5.1, or 256, or whatever I've got here. It could be 5.000001 or whatever. But it can't be 5, because x is greater than 5. Down here it's greater than or equal to. In this one we've got x is less than. Now this is a sign we haven't met before. It's just the reverse of this one up here. This is greater than. This one down here is less than. The x is smaller than the 9. But in this case it's less than or equal to. So x, in this case, x can equal any number less than 9. For example, x could be 6, or 2.1, or minus 23, or 0, or 0.4. It could be 9. It can equal 9 because it is x is less than or equal to 9. So it could be have the value 9, or it can have any value smaller than 9. These are important points, and make sure you're clear about these. If x equals 1, then x plus 2 is equal to 3. Think about it. If x is equal to 1, so that becomes a 1. 1 plus 2 equals 3. So x plus 2, 3, and that's balanced. If x equals 2, then x plus 2 is greater than 3. In other words, we've got 4 on this side, because x equals 2. So we've got 2 plus 2 is 4. 4 is greater than 3, so it tips it up. It's no longer balanced. This side is heavier. If x equals 0, then we've got x plus 2, which is just 2, because 0 plus 2 is just 2. So if x is equal to 0, we'd have 2 on one side and 3 on the other side, so it tips up the other way. These are the three signs you need to remember. On the left we've got equal, equal to. That's very important and it's quite common. This one here may be new for some people. This one is greater than, and this one here is less than. Just remember which way around they're pointing. That's greater than, less than. And that's all we're going to do in this session. We've done quite a bit, so look over it a few times and make sure you have good understanding of what we've done. This is the fundamentals of algebra. This is introducing the topic. But let's leave it at that then and say thank you for watching.